We learn from quantum theory that the vacuum is not empty. The vacuum of a quantum field, such as an electromagnetic field, undergoes quantum fluctuations. Those fluctuations look locally random, but the fluctuations in different points of space and time contain non-classical correlations. Consider, for example, two atoms which couple to the electromagnetic field. If the two atoms are allowed to exchange information, for example, if they can exchange photons, it is not surprising that they can get entangled. However, what if the two initially uncorrelated atoms remain space-like separated during the whole life, so that they can never exchange information? These two atoms cannot know about the existence of each other. As such, one might think that these two atoms, which cannot exchange real photons, will not be able to get entangled through the interaction with a quantum field. Nevertheless, it was shown that, perhaps surprisingly, two space-like separated atoms that interact locally with an electromagnetic field can also become entangled. This is true even if they cannot know about each other's existence or exchange any photons. This phenomenon has become known as entanglement harvesting. To understand entanglement harvesting, we can think of the following scenario. Suppose that we want to get two harmonic oscillators, A and B, entangled. A and B cannot have direct interaction. The resource we're given to accomplish that task is a lattice of coupled harmonic oscillators in its ground state, to which we can couple A and B locally. There are two ways to get the atoms entangled with such a setup. First, the most intuitive one, is to let A and B interact with the lattice and create excitations, that is, phonons, that propagate at the speed of sound from A to B and from B to A, resulting in A and B acquiring correlations. This is limited by the speed of sound. But there is another possibility. Due to the interaction of the lattice of oscillators, the ground state of the lattice is not simply the product of the individual ground states. The ground state contains entanglement between pairs of distant lattice nodes. A and B can couple to these nodes and swap the entanglement from the nodes to themselves through local interactions. This results in A and B gaining entanglement. This mechanism, in which A and B harvest entanglement from the lattice, does not involve exchange of information between A and B, thus not being limited by the speed of sound. A quantum field, such as the electromagnetic field, can be understood as the continuum limit of such a lattice. The electromagnetic vacuum contains entanglement between space-like separated regions. The two atoms interacting locally with the field harvest the quantum entanglement of the ground state of the field. Entanglement harvesting has potential applications ranging from quantum resource generation, metrology, and communication to the very understanding of the background structure of spacetime. However, its experimental realization requires of the establishment of a common reference frame between A and B. This raises the following question. Is entanglement harvesting robust under imprecisions in the spacetime localization of A and B? Is it realizable under realistic imprecisions in A and B's positioning and timing measurement devices? Here we show that entanglement harvesting is robust under imprecisions in the determination of the relative spacetime positioning of A and B. Specifically, we show that the protocol is robust if imprecision in spatial positioning and close synchronization are much smaller than the spatial separation between the detectors. This, in principle, guarantees robustness if the imprecision is comparable to a few times the size of the detectors, which suggests entanglement harvesting could be explored for tabletop experiments. On the other hand, keeping the effects of this imprecision under control would be demanding on astronomical scales, which may have implications in entanglement in cosmological scenarios.